Yeah, so I don't know, we'll do it randomly this semester. Once in a while. All right, so more proofs. I want to do a simple one. All right. So here's a statement. If, so let's call it some property. Let's call it property 1 for today. I know we have property 1 from last week, but property 1, if P divides N, then P divides the product of N M for all integers M. So again, N is an integer, P divides N, so if you multiply N by anything else, P will still divide that, right? I mean, does that make sense? Just a numerical example of what this is trying to say. Let's say 3 divides 6, so then 3 will divide any multiple of 6, right? Multiply 6 by anything, then 3 divides 6 times 5, right? 3 divides 30. So regardless of what this number is right here, 3 will always divide that product. So for any integer M. There is a shortcut in order to write for all integers M. Remember we were talking about different little math symbols, and do you remember the math symbol for there exists? Yeah, like a backwards capital E. There is a symbol for all integers, and it's an upside down capital A. So instead of writing for all integers M, I can write it like this: for all M, so M is an integer. So an upside down A, that stands for all. Backwards E stands for there exists, so not for all, but for all is an upside down A. Isn't that fun? The math symbols are creative right now. So anyway, but the proof is very simple, right? Remember, we're just going to use the definition for divisibility. So all we have to show that we can write NM as a multiple of P, right? That's the definition. So the proof is actually very quick. We can say that since P divides N, there exists some integer Q1 so that N equals P times Q1. Or Q1 times P, we're writing it like that. So this is the definition of divisibility. Oh, Bradley. Okay. Is that all right? Oh, homework is due on Wednesday, right?
What?
Homework was due on Wednesday.
Yeah.
Okay. We changed the date because we kind of went off track on Friday.
He wasn't even there on Friday. So
I know, but I changed it on Canvas, so that's, I changed it on Canvas. No. I would, no, don't, that's breadless. I'm not saying this is going to be any good. Oh, I'm on record saying this now, so hey. Anyways, are you with me so far? That's by definition. This is by definition. Definition of divisibility, right? Just any integer, some integer, right? Because again, we know that P divides N, therefore we can write N as a multiple of P. That's all I'm saying, right? And we're using those subscripts just in case we're going to run out of letters, right? Well, now, look at what we're trying to prove. We're trying to prove that P divides NM, so we can say, therefore, NM equals, well, I know that N equals 2, so I can substitute that in for N. So I'll get Q1 times P times M, right? Or I can say like this, P times Q1M, so this is some integer, Q, so therefore we get P times Q. So NM is written as a multiple of P. So therefore P divides NM. Again, all I'm using is the definition of divisibility. And it's not the only way to prove it, but that's kind of in the ballpark. Use the definition twice. So again, in order to show that something divides something else, you have to express whatever you're trying to divide by as a multiple of the divisor. And that's it. That's the definition of divisibility. Right? Let's do a fun problem. Fun problem. So I want us to find all 5-digit numbers that are divisible by 45 and first 4 digits are consecutive. Like 1, 2, 3, 4, and then whatever, right? Because remember, it's a 5-digit number. So, for example, 1, 2, 3, 4, 7. First 4 digits are consecutive, and the whole thing is divisible by 45. Probably not this one, because I just totally made it up. But that's the idea. The first 4 are consecutive, the last one, whatever. But the whole thing is divisible by 45. Does that make sense? I want to find all numbers like that that are divisible by 45, and first 4 digits are consecutive. Does the question make sense? Well, that's the thing. That's what we're about to try with sheer power of logic. Okay? So, we just proved something. We proved that if P divides N, then P divides the product of N and something else, right? We just proved that. So here's the proof. So let 45 divide N. So we know our number that we're looking for is divisible by 45, right? So that's given. You agree with that? Now also, what else divides 45? Can you give me some divisors of 45? What? Yeah, give me some fun ones. What are the most 2 obvious ones? 9 and 6? No. What? No, divide 45. What numbers divide 45? He was on the right path. He gave me a 9 and 5 and 9, right? So we can also say since 5 divide 45 by the property we just proved, by property 1, 5 has to divide our number, right? You agree with that? Also, since 9 divide 45 by property 1, 9 divides our number n. So we kind of simplified our problem. We're looking for a number that is divisible by 5 and 9. Okay, so that kind of simplified us, because thinking about divisibility of 45 is a little messy. But it has to be divisible by 5 and 9. Now, do you remember we kind of talked about this last week? How do you know whether a number is divisible by 5? Ends in 0, 5, right? Keep that in mind. How do you know whether a number is divisible by 9? We actually proved that on Wednesday. No, don't use your fingers. We proved that. How do you know whether a number is divisible by 9? It's in your notes from Wednesday, I think. Right, if the sum of all digits is divisible by 9, then. So it's same as 3. So, what I can say now, let n equal A, B, C, D, E. So these are my 5 digits. So we agreed we're going to use this notation. We're going to put a little bar on top to show that it's not a product of A, B, C, D, and E. These are my 5 digits, right? So there are only 2 options for E. E is either 0 or 5, right? As you said, since 5 divides, so make a note, since 5 divides n, E is either 0 or 5, right? So the last digit has to be the 0 or 5, okay? So we're going to do it in 2 cases. We're going to look at case 1, let E equal 0, and then find A, B, C, and D. And we're going to take a look at case 2, let E equals 5, and we'll find A, B, C, D to make sure that it's divisible by 9 now, right? Because we have the divisibility by 5 is given. So case 1, E equals 0, so therefore n equals A, B, C, D, 0, like that. These are my digits. And also n is divisible by 9, right? That's what we agreed on. N has to be divisible by 5, so 0 made sure that. But also n is divisible by 9, so since 9 divides n, we know that 9 divides the sum of A plus B plus C plus D plus 0. So the sum of these digits has to be divisible by 9. That's the test for divisibility by 9, as we proved on Wednesday, right? No reason to put plus 0, because 0 doesn't do anything. So we can just say or. A plus B plus C plus D. So the sum of 4 digits, right? The sum of the first 4 digits. What do we know about these first 4 digits? Do we have another condition on the first 4 digits? It's, you know, in the body of the problem. What else has to happen? Divisibility by 45, and there is another thing. It says right there. Have to be consecutive, right? So 1, 2, 3, 4, right? Or 4, 5, 6, 7. So B is 1 greater than A, and C is greater than A by 2, and D is greater than A by 3, if they're consecutive, right? So I can just say that B equals A plus 1, C equals A plus 2, D equals A plus 3. That's what makes them consecutive, right? So if I actually make that substitution, so A plus B plus C plus D equals A plus 1 plus A plus 2 plus A plus 3, right? So if I combine, if I simplify that, I'll get 4A plus 6. right? So therefore, 9 divides 4a plus 6. So all I have to do is to find a, right? If I find a, then I'll know b, c, and d. And then I'm done, because I already know e. E equals 0 in this case. Okay? All right, so the only way to do that one is by trial and error. Let's do it verbally. First of all, can a even equal 0? Can you have a 5-digit number starting with 0? No. So can a equals 1? If a equals 1, you get 10. Does 9 divide 10? No, so a cannot equal 1. If a equals 2, we'll get what? 8 plus 6, 14. 9 divides 14? What? What do you... 9 divides 14? No. A equals 3. 12 plus 6 is 18. 9 divides 18? So, okay, keep 3 in mind. 3 can work. Is there anything else can work? 4. 4 times 4 is whatever. Plus 6 is 22. Does 9 divides 22? No. How about 5? If I take 5, 5 times 4 is 20. 20 plus 6 is 26. No. 6. 6 times 4 plus 6. 9 divides? No. 7. Can a equal 7? If a equals 7, then it's 7, 8, 9. Then d has to be 10. That's impossible, right? So the highest value that a can be is 6. A ranges between 1 and 6. Do you agree with that? Because I cannot have a digit, single digit, representing 2 digits. So, what? No. Yeah, in this case, a only equals 3, but the possibilities for a is from 1 through 6. Otherwise, we don't get any consecutive digits. So, yeah, so the only one that worked, so by examination, so this is why recordings are important, because I just talked for 5 minutes without writing anything down. By examination, a equals 3. So therefore, n equals 3, 4, 5, 6. 4 consecutive digits, 0. Here we go. We agreed that the last one was 0, right? So that's the only one that's divisible by 9 and 5. Now, and ends in 0. There is another case. There's case 2. So don't forget that. Case 2, that's when e equals 5. So we did the problem when the last digit was 0. Now we're going to do when the last digit is 5, because that's, divisibility by 5. So therefore, n equals a, b, c, d, 5. Right? So the sum of these digits has to be divisible by 9. And therefore, 9 divides the sum a plus b plus c plus d plus 5. Just like before, we played with a plus b plus c plus d. That gave us 4a plus 6, right? That's the sum of the 4 digits. Then plus 5, we'll get 9 divides 4a plus 11. That's what we need to do. We need to find an a. So 4a plus 11 is divisible by 9, right? So we'll do the same thing. We'll do by examination again as before. A can only range from 1 to 6. A cannot be greater than 6, so we won't get the consecutive integers. So let's go. A equals 1. 15, right? Doesn't work. A equals 2. 19, right? Doesn't work. A equals 3. 12, 33, doesn't work. A equals 4. 16 plus 11, 27. So 4 works, right? A equals 5. 20 plus 11, 31. Does not work. A equals 6. 24 plus 11, 35. Doesn't work. So the only one that worked was it 4? 16, 27. So A equals 4. And our digit is 4, 5, 6, 7, and then 5. So the only two numbers that are divisible by 45 and first four consecutive integers, first four digits, I should say, are consecutive. Isn't that fun? You know, it was kind of weird at the beginning, but then we just started breaking it down. And this is totally legitimate, do it by cases. You're kind of taking everything that you know in this. So you said either ends in 0, ends in 5. These are my two cases. Let's look at the case when it ends in 0. Let's look at the case when it ends in 5, and then take another piece of information and then see what we can do. This is a fun problem. Yeah? So there are only two numbers like that. Okay. We did write the rationals and irrationals, right? We introduced. Yeah, we did. Did we write down? Yeah, what are the irrationals? So can you give me some examples of irrational numbers? Yeah, pi. Square root of 2. By the way, do you guys just totally random? I'm going off topic a little bit, but there's something fun happening. Who knows pi? What is pi? Well, can you give me the digits? 3.141592, right? I think it's 92, like 6, 4, or 5. Let's see. I'm started rounding at some point. Where's pi? Pi. 92653. So, and so forth. Do you know that we celebrate Pi Day? Do you know there is a Pi Day? March 14th. But this year, we have a Pi Day of the century because it's March 14th, 15th year. So at 9:26:53 seconds, we have the largest Pi Day of the century. And I don't know what it falls on. It happens once every 100 years. They should get 3, 14, 15 lined up like that. So aren't you lucky? And it's on Saturday. So we won't be able to do the big countdown in the class, but because it will happen during our class. So 9:26:53 seconds a.m. on March 14th, we have a Pi Day of the century. It's a big day. We'll go celebrate and stuff. That's kind of cool, right? Anyways, but square root of 2. You just mentioned square root of 2 is irrational. So square root of 2 is irrational. On your homework that Bradley just turned in, you have to prove that square root of 3 is irrational. Okay, so I'm going to prove the square root of 2 is irrational, and then you really just have to make a few very slight changes to show the square root of 3 is irrational. Now, before we prove that, I need a little preliminary result. Okay? Usually in math, we're trying to prove, let's say this is a theorem, square root of 2 is irrational. In order to prove this big theorem, we might need few little theorems to prove that. Those little theorems are called lemmas. Okay? A direct result from a theorem is called corollary. If you just say, oh, well, this theorem, but then clearly it implies something else, so that's a corollary. But we need a little lemma that n is even if and only if n squared is even. Now remember that if and only if thing, that means two-way street. So we have to prove if n is even, then n squared is even. And we also have to prove if n squared is even, then n has to be even. So it's a two-way street. One way is really easy. It's easy to prove if n is even, then n squared is even. This is easy to prove. Okay? Because again, we know that n is even, therefore n equals 2 times something else. So n equals 2k. And you square that, you get 4k squared, which is even because of the 4, right? So the proof is very simple here. Since n is even, there exists an integer k, so that n equals 2k. Right? That's the definition of even. Right? Right? That's how we define even. So therefore, n squared equals 2k squared, which is 4k squared, which is 2 times 2k squared. So 2 times an integer. So that gives you an even number, right? That's the definition of even. So therefore, n squared is even. And we're done. Is that okay? So that was pretty straightforward. You go 2k, you square 2k, you get 4k squared, clearly even. 4k squared can be expressed as 2 times something else. That's the definition of even. Now to go backwards, to show that if n squared is even, then n has to be even. It's a little harder. Okay? To show the other direction, if n squared is even, then n is even. How can we do that? Think about it. From everything that we've done so far, you should at least be able to get started, write a few sentences, and hopefully get stuck, and then realize that it's not easy. But how would you get started? You know, what do we know? This is given, right? Well, n squared equals 2k, right? Because we know that n squared is even. We need to prove that n equals 2k, right? That's the idea. You're saying that, well, so since, don't write this down yet. Since n squared is even, there exists an integer k, so that n squared equals 2k, right? Now what you need to prove, your last line in the proof, remember therefore n is even, that's your last line in the proof. So the line before that should be there exists k, well not k, but basically the line before that should be n equals 2 times some integer. That's what you're trying to get. If you can get n equals 2 times something, then n is even. Now how do you fill in the in-between part? Do you see that it's hard to do? Because you have to go from n squared to n, means you have to take some kind of a square root maybe. So you're going to end up with a square root of 2 times k, and the square root of 2, as Arthur pointed out, is irrational. We haven't proved that yet, but so you're going to have a square root of 2 and a square root of k, and somehow you have to conclude that that's even. And that's not easy. I mean, you have to make some really messed up arguments that we might not be able to do that. Chris, how's that? Okay. So in these situations, what we tried to do, the direct proof, and we kind of got to the point that's really sneaky, really tricky. Well, we should abandon the direct proof and try indirect proof. And we did an indirect proof on Wednesday. That was a proof by contradiction. Well, let's do the contradiction proof. Okay? Because look, n is either even or odd, right? There's no third option. There's no numbers that are neither odd nor even. Each integer is either even or odd, right? So if I want to use contradiction, I'm going to assume the opposite. I'm going to say, well, let n be odd. Okay? And I'm going to see what that's going to lead me. And if I reach a contradiction, therefore n is odd is wrong, therefore n has to be even. Remember that? That's how we did contradiction proofs? Yeah. So we're going to do a proof by contradiction. So we're going to refresh that memory, and then we're going to prove that square root of 2 is irrational, also by contradiction. So we're going to do a proof by contradiction. So proof by contradiction. So again, proof by contradiction works in cases where there are only two things possible. It's either this or that. Or if there are three things possible, you kind of already knocked one of them out. Okay, that one is impossible. And then, does that make sense? Like, what is moon made out of? Is moon a rocky object or a gas object or a cheese object? There go three options. So we can knock the cheese out, and then you do the contradiction on the gas and rock. I don't know. I hope not. It would be nice if moon is made out of cheese, but I think they've tested that one. But anyway, so for the sake of contradiction, that's how we started those proofs. For the sake of contradiction, assume that n is odd, right? Therefore, if n is odd, therefore n equals 2k plus 1. That's the definition of an odd number for some integer k, right? That's the definition of odd. Therefore, n squared equals 2k plus 1 squared, right? Because we're trying to get to n squared. We're studying the relationship between n and n squared. So now we're going to use our algebra. The way we square 2k plus 1, you can either FOIL or you can use the formula for squaring a sum, right? So that's 4k squared plus 4k plus 1. That's how you square a sum. You all remember that? That was a big deal in algebra and in the courses before algebra. If you don't know what just happened, FOIL. Write out 2k plus 1 times 2k plus 1 and FOIL. You'll get that. But the point is, look, I can certainly factor out a 2 out of the first two terms, right? I can write it as 2 times 2k squared plus 2k plus 1. This is some integer. So I have n squared equals 2 times an integer plus 1. So is n squared odd or even if it's written as 2 times something plus 1? Odd. So therefore, n squared is odd. Right? Have we reached the contradiction? It's given to me that n squared is even. Right? So that contradicts whatever was given to me. So therefore, my assumption was wrong. N has to be, n is not odd, so n is even. That's a contradiction. Contradiction squared is even by, whatever is given to us, by the given part. Therefore, n is not odd. Therefore, n is even. QED. So sometimes direct proofs are harder and the contradiction proofs are a lot easier. So we run a contradiction. We assume the opposite of what we were trying to prove, and that contradicted the part that was given to us. That meant the world just collided, so whatever we assumed was wrong. So the opposite of what we assumed had to be right, because n is either odd or even. If there is other options, then contradiction does not work. If n is odd, even, or a monkey, then, it could be a monkey. So I don't know, right? Because I got stuck. Yeah, right. So I mean that lets you know that you're allowed to do proof by contradiction. You have two options. And again, you can have more than two options, but if you knock out some of them, right? It's like when you do a multiple choice test. You have 5 options, but 2 of them are basically nonsense, and you knock them out, you're down to 3, and then you start guessing. Kind of that. But it's a contradiction proof is very simple in this case. It's the same as our previous direct proof. All right. So we're going to need this result, this little lemma, in order to prove that square root of 2 is irrational. Okay? So here's, let me go back. So again, in order for me to prove that square root of 2 is irrational, I'm going to do it by contradiction. Because again, every real number is either rational or irrational. There's no middle ground. They're completely separated. You cannot have a number that's both rational and irrational, right? Because the definition of rational, I can write it as a ratio of 2 integers, a fraction. Definition of irrational, I cannot write it as a ratio of 2 integers, so they're mutually exclusive. And every real number is either rational or irrational. So in order for me to prove that square root of 2 is irrational, I'm going to assume that it's rational and then show that, well, that's not going to work. Okay? So then I'm going to reach a contradiction. I'm going to say square root of 2 is not rational, therefore it must be irrational. Okay? But first of all, just a quick note, the square root of 2 is still a real number. It exists, it lives on a real number line. You can walk to your local lumber store and ask for square root of 2 feet of whatever. They'll kick you out, but you can ask for that. That's measurable. You can construct a stick that's square root of 2 feet long without measuring it, because you cannot measure square root of 2 because it's irrational. That decimal goes on forever, but you can build, right? Do you know how to build square root of 2? Just a side note. So square root of 2 is irrational. Now, the nice way to define a real number is that if you can find it on a number line. So if I can measure square root of 2, then it's rational. Now, pi, I cannot measure pi, but I can still find pi. Right? I'll just need to draw a circle of radius 1, and then it's 2 pi circumference, and take half of it, that's pi. Boom, put it on a number line. But with the square root of 2, I can go to the lumber yard and I can ask them for 2 sticks, or for 3 sticks. I'm going to ask for 1 foot long stick. That should be able to do that, right? I'm going to ask you for another 1 foot long stick. They should be able to do that. I'm just going to ask them for a randomly large stick, 5 feet long. So I'm going to do 1 foot here, 1 foot there, and I'm going to put the long one like that and just make a cut. Okay? By the Pythagorean theorem, this c squared equals 1 squared plus 1 squared, right? So c squared equals 2. So therefore c has to be square root of 2. So this is square root of 2. So I can build square root of 2. So it's real, I can touch it. Okay? That's a whole other argument whether irrational numbers are real or not, but let's say they are. So I just build square root of 2. Now,
Is that a way to prove that?
no. This is just to show that it's real.
Okay, yeah. But is that a clear proof?
No.
It's a lot more visual. I like that way.
Well, that has nothing to do with its irrationality. It has to do with its, reality. But to prove it, yeah, it's going to be all kinds of abstract. So for the sake of contradiction, we're going to assume that square root of 2 is not rational, so it's rational. So for the sake of contradiction, assume that square root of 2 is rational. In other words, remember the capital Q, weird-looking Q, that's a set of rational numbers. So square root of 2 is a member of Q. Right? So if it's rational, then I can write it as a fraction. Therefore, there are two integers, so square root of 2 equals the ratio of those two integers. So therefore, there exist two integers, let's call them P and Q, so that square root of 2 equals P over Q. That's definition of rational numbers. I can write it as a ratio of two integers. Oh, it's a set of rational numbers. Q for quotients. So that's what we're assuming right now. Okay, and that's what we're going to... Something is going to go horribly wrong in this proof. And that's how you know we've reached the contradiction. Question? Now, I want to make a note. There is infinitely many ways you can write a rational number. For example, don't write this down. Is 5 a rational number? Say yes, because I can write 5 as a ratio of what? What? 5 over 1? Is that the unique way of doing that? Is there any other ways I can write it? 10 over 2, negative 35 over negative 7, right? There are infinitely many ways I can express each rational number. So that's going to cause a problem. I'm going to assume then that P over Q fraction is reduced, that it's in the most reduced form. So P and Q do not have any common factors. Because if they do, I can reduce it. You agree with that? I mean, I can always reduce my fractions. So we're going to assume that P and Q are in the most reduced form. So I'm going to say where P and Q are relative primes. That means that they do not have any common multiples, meaning P and Q do not have common multiples. Is that okay of a statement? Because if they do, we can always reduce. So basically all I'm saying is we can reduce our fractions. No matter how much you hate that part, we can always reduce our fractions to the most simplified form. You all with me on that? That's an important thing, by the way, in this proof. Okay. Now let's keep going. Well, since square root of 2 equals P over Q, I can say that if you square both sides, we get 2 therefore 2 equals P squared over Q squared. Right? If the square root of 2 equals P over Q, then 2 equals P squared over Q squared. Right? Therefore, p squared equals 2q squared. Just, rearranging the fraction. Can I say that p squared is even? Because p squared right now equals 2 times q squared. So is it even? P squared equals 2 times q squared. So is p squared even? Yes. So therefore, p squared is even. Therefore, p is even. By the lemma we just proved. By lemma. Right? If p squared is even, then the number that you're squaring is even. How's that? So far? So therefore, p equals 2k. If p is even, I can always write it as 2 times k for some integer k. So far, so good? So I'm going to take this expression and I'm going to substitute in here for p. Because I know p right now equals 2k. So therefore, I have 2k squared equals 2q squared when I substitute 2k for p. Right? Therefore, now I'm just using algebra. I get 4k squared equals 2q squared. When you square 2k, you get 4k squared. Yeah? Divide both sides by 2. I can reduce by 2. Therefore, 2k squared equals q squared. Dividing both sides by 2. Yeah. Well, not yet. We're making the same argument. I got q squared equals 2k squared. What can you conclude about q squared? Is that even? Is q squared even? Q squared equals 2 times something else. So is it even? What's the definition of even numbers? Or 2 times something else, right? That's how we write it. That's how we do this whole 2k thing, right? If something is even, you can always write it as 2k. So if q squared is 2 times something else, q squared is even. So I can say that, therefore, q squared is even. Right? So what can I say about q itself? By the lemma we just proved, if q squared is even, what about q? Is q even or odd? Even, right? We proved that. So therefore, q is even. And this is where you have to start wondering a bit. No matter what, p is even and q is even, right? So I have a fraction, numerator is always even and denominator is always even. Can that happen? Can a fraction have an even numerator and even denominator? Yeah, so what can I do with that fraction? Simplify it until it no longer has an even. But this says I cannot. No matter what I do, I will always have an even numerator, even denominator. I made this note that p and q are relative primes because we can always reduce them. So p and q already in the most reduced form And all of a sudden, I'm getting that they're both even. So they're not relative primes, they're multiples of 2. So I'm contradicting the ability to reduce fractions. So what just happened, the whole structure of arithmetic collapsed. That we cannot reduce fractions no matter how hard you try. You'll always have an even numerator and even denominator in this case, which is impossible, right? That's my contradiction. P and Q cannot both be even. Because if they are, I can reduce them to the point where at least one of them is not even. But this says, no, they're always going to be even. So that's my contradiction. Therefore, my assumption is wrong. Therefore, square root of 2 has to be irrational. So that's a contradiction. Sometimes we write contradictions like that. We have two arguments that collapsed. So therefore, contradiction, I cannot write today. Both P and Q cannot be even. Therefore, assumption was wrong. Therefore, square root of 2 is not rational. So it's irrational. QED. It's a pretty messed up proof, and we really kind of hung on this fact that fractions are reducible. Because we assume that it can. Because we assume if it's rational, then it can equal P over Q. That's the definition of rational numbers. Rational numbers can be expressed as ratio of two integers. Right? So that's what we did. P and Q are those two integers. And we said that, well, they're equal in many ways you can do that. Let's reduce them. So P and Q are reduced. And then we went through the proof, and we got to the point where both P and Q are even. They're both multiples of 2. That was our contradiction. That contradicted our ability to reduce fractions. Okay? So you have to do the same thing only for the square root of 3. So you'll do the same thing, only now it's not even. They're both divisible by 3. So then you're going to say, well, P is a multiple of 3 and Q is a multiple of 3. No matter how hard you try to reduce them, you're always going to have multiples of 3 in the numerator and denominator. Okay? Isn't that fun, Arthur? This is good. How's your brain doing? Is your brain doing things that it hasn't done before? The way it's thinking right now? That's the purpose. We're running backwards. How many of you heard of Fermat's last theorem? This is the sexiest sentence in mathematics, by the way. Fermat's last theorem. Google it. Arguably the sexiest sentence in the whole of mathematics. I'm not making this up. So Fermat was this lawyer, French lawyer in 1600s, who for fun did a whole bunch of math. He was reading books on mathematics. He was heavily involved in a branch of mathematics called number theory. This is where you just deal with natural numbers. This is the thing that has very few applications, so you cannot really get paid for doing number theory, but it's a lot of fun. But if you're a lawyer, you can certainly do math for fun, because you're not gonna, you're not gonna support your family by doing number theory, but lawyering you can probably do, so you do some stuff on the side. And he created, there are many theorems that devoted to Fermat in that branch of mathematics. So he's actually, we consider him, nobody cares about his lawyering skills anymore. He is one of the big mathematicians in history of math. And when he passed away, his son was going through Fermat's library of books and kind of looking at his notes. And he used to, like, he'll take a book and he'll just make little notes on the margin of the book. And he wrote this theorem that a to the power n plus b to the power n equals c to the power n, has no integer solution for n greater than 2. Now, meaning, a, b, and c are integers. If we allow them to be anything other than that, or actually even natural numbers. Go ahead. Yeah, because I didn't write it right. Has no integer solutions. Solutions, or solution for that matter, for n greater than 2. So n, if n, the power is greater than 2, then you won't be able to find any 3 integers that satisfy that. If n equals 2, then it's your, if n equals 2, then it's things like 3 squared plus 4 squared equals 5 squared. That works. These are your Pythagorean triplets, we call them. So that works. But if you go n greater than 2, you won't be able to find 3 integers that will work. Okay? And he wrote that thing on the margin of his book, and below, and I quote, he wrote, I have a marvelous proof to that theorem, but I don't have enough space to write it down on that little margin. Because I didn't have enough space to fit it in. So they just saw that after he died many years. So they've been trying to prove that for about 350 years after his death. They finally did. That thing was proven in 1994. The math went into places that were not available to good old Fermat. The math, actually, there was a whole branches of math just to prove that theorem. There were some suicides involved. It was one of those things. It was like everybody was after that. That was the hottest thing because it sounds so simple. And that guy claimed that he has this marvelous little proof. Now, the proof of that thing is ridiculously long. It was like 900 pages long that involves different, brand new, hottest branches of mathematics just to prove that. But yeah. Now, so it was proven by a professor from Princeton University. His name is Andrew Wiles. He proved that in 1994. Yeah, maybe. Well, yeah. So maybe, yeah, because he's famous. He probably got that $1 million prize for some of those open theorems, but it wasn't, yeah. He didn't care about that at that point because he probably made like McDonald's wages, if assuming how much time he put into proving that theorem and getting just $1 million out of that. So he was getting paid like $5 an hour. But if that's possible, I don't know. I'm just making stuff up. So now with that theorem, I can actually prove that any root of 2 is irrational. Not just the square root of 2, but the 7th root of 2, 11th root of 2. Every root of 2 is irrational using that theorem. Now, are any of you familiar with this TV program that's probably older than you are called The Simpsons? Do you know that the writing staff is full of mathematicians in that show? They like to, you know how sometimes Homer has his psychedelic dreams when he's walking around in like 4 dimensions and such? They like to throw this theorem, they'll write like some obscure large number to like power 17 plus some obscure large number to the power 17 equals another obscure large number to the power 17, as if Homer is dreaming of a specific counterexamples to that theorem. And if you plug it in your calculator, those numbers are so large, your calculator starts rounding, so it looks like, oh, it actually works. So there are close numbers that make it work. You have numbers in like Brazilians, and then you're off by like a couple billion, so it's like, hey, it's basically the same, right? I mean, I can probably go on, I can Google this, the Fermat's last theorem and The Simpsons. Oh yeah, happy Martin Luther King Day. So, what was I going for? So Fermat's last theorem, you see, and Simpsons. So here we go. Here's Homer kind of doing his thing. Homer Simpson versus Pierre de Fermat. Okay, I cannot. Yeah. Never mind.
To deal with the devil, and part of that deal is that he can keep his soul if the devil can persuade with the wizard of Evergreen Terrace. So Homer Simpson wants to become an inventor, and he has a blackboard, he's seen scribbling things on the blackboard. And one of the equations that Homer Simpson writes on the blackboard is unattacked.
Okay, you see that? Large number to the power 12 plus large number to the power 12 equals some other large number to the power 12. So that's Fermat's last theorem. Of course, there's something about donuts. This is what he's doing right here. That's another big theorem, that a donut is really a sphere. If you're thinking, we don't have Andy here. She's a donut person, but that's another branch of mathematics. Oh, she's listening because she has to record that. There's another branch of mathematics called topology, and this is he just talking about shape. So topologically speaking, there's no difference between a donut and a sphere. Now there was it was one of those 300-year-old theorems, and the guy from St. Petersburg, his last name was Pillerman. He proved it, and he was one of those, like the stereotypical math dudes. He was like in his 50s, living with his mother type of thing, and he was awarded what is called the Fields Medal in math. You know what that is? Well, do you know the Nobel Prize? There's no Nobel Prize for mathematicians. It's just all other things except for math. And it's awarded every year. Now, so they did the Fields Medal, which is kind of the Nobel Prize for math, only it's awarded every 4 years. So he got that for proof of that, what Homer is writing there. And he refused the prize. It was like a whole bunch of money, and plus, it's more than a Nobel Prize, and he just didn't want to accept it. I don't know. He was a very strange guy. Type of things like I don't need your like millions of euros. I got my mom type of deal. But anyways, don't quote me on that. But so yeah, so there, and he kind of talks about there are a few other episodes where here's Homer.
We're looking at 4-digit numbers to the 12th power, so we're looking at 48-digit numbers. And so if they're out by millions and millions, that's only a tiny amount because we're looking at such massive digits. And so on most calculators, you won't see the error. If you were really smart, you wouldn't need a calculator to know there was something wrong in one of these. If you look at the second one, now this one is obviously wrong. Now the reason it's obviously wrong is because this is an even number. It has a lunchbox with Anatoly Karpov's picture on it. Now, I remember Anatoly Karpov as a great chess player of the early 70s. Now, I get somebody on this station. When we're we're looking at it kind of proportionally, is it in here?
Anyways, so yeah, it's a very famous thing, but now we can prove that any root of 2 is irrational. So all you have to do is to say, well, you can say that nth root of 2 is irrational That's what I want to prove. Any root of 2 is rational. So I'm going to do 2 cases. N equals 2. So that really means square root of 2, right? We'll never write a little 2 above, right? So is irrational. So we just proved that. Now for n greater than 2, because there are 2 cases, right? If I want to prove for all n, I can say, well, 2, and then everything greater than 2. For n equals 1, doesn't make sense, right? 2 is... So by contradiction, don't write this down. I'm going to show you really fast. So by contradiction, let nth root of 2 be rational, right? Okay, so therefore, nth root of 2 equals p over q, as we just did, where p and q are integers. Well, I should say natural numbers, really, in this case. Natural numbers. That's the definition of rational, right? Just like we did before. So therefore, if I raise both sides to the power n, I get 2 equals p to the power n over q to the power n, right? If I raise both sides to the power n, q is the radical. So if I multiply both sides, I get 2 q to the power n equals p to the power n, right? I'm just doing algebra. Well, what does it mean if you have 2 times something? That means it's the same thing as saying it's q to the n plus q to the n equals p to the n, right? That's what 2 means. Well, that's precisely the statement of Fermat's last theorem for n greater than 2. Fermat's last theorem states that there are no natural numbers that make that work. P and q cannot be natural numbers. It contradicts Fermat's last theorem. So boom, we're done. Contradicting Fermat's last theorem. We weren't able to do that, what, 20 years ago. Now we can, since 1994. So it contradicts Fermat's last theorem. We actually call it FLT for Fermat's last theorem. So therefore, all of them are irrational. Isn't that cool? Oh, he died a long time ago. Yeah. Not really. He died. We don't know when he wrote that theorem. I mean, maybe we do. I don't know the full history. But the theorem was discovered after his death, that he kind of wrote it down. But they weren't able to prove it for 350 years or so. All right. So yeah, so the Simpsons, they like to geek out about that type of stuff. Okay, so a few things. Just a little housekeeping. These are boring things. I mean, assuming everything prior to that was a whole lot of fun. Are you with me? Yeah, thought I was losing you there for a second. So we need to talk about LCM, least common multiples. You know what that is? Least common multiple. The same as least common denominator, really. That's the same idea. So the way you do that, if you want to find LCM of 2 integers, LCM of n and m, where n and m are some natural numbers, you do it in 2 steps. 1, perform prime factorization of both. So you break them down in primes. And 2, take each distinct prime raised to the highest power. Now, what I mean by that, let me do a numerical example. So, LCM for 16 and 18. So, basically the idea is, just picture you have 2 fractions. One has 16 in the denominator, the other one has 18 in the denominator. You're trying to find the least common denominator. That's really what's happening. Now, it's hard to just see the LCD or the LCM for 16 and 18. So we can follow these steps. Now, the prime factorization of each one of these numbers, 16 is 2 to the power 4, right? That's the prime of that. Now, 18 is 2 times 3 squared. 18 is 2 times 9, 9 is 3 squared. So that's prime factorization of both of these numbers. Now, the LCM then, using these 2 results, so remember, we need 2, right? 2 is a factor. What is the highest power of 2 that we see? 4, so I need 2 to the power 4. I see a 3 is one of the factors. What is the highest power of 3? 2, so this is my LCM. You take everything to the highest power. So that's 16 times 9, so it's 144. So that is the least common multiple of 16 and 18. Now, the other item that we talk about, is, in addition to LCM, is GCF. Yeah. The greatest common factor. So there you do the same thing. You take both numbers, you do the prime factorization first, but instead of taking everything to the highest power, you only take the common factors to the lowest power. So now a number has to be in both factorizations, and you pick the smallest one. So for the GCF of two numbers, one, you need prime factorization of n and m, and two, you need common factors to lowest power. So now something has to be shared. Okay? So if I do the same thing, GCF of 16 and 18, and I already know that 16 is 2 to the 4th, and 18 is 2 times 3 squared. Is there a common prime between these two numbers? 2. And what is the lowest power of 2 that we see? 1. So that's it. So GCF here is 2. Now, take a look at this. If I go 144 times 2, 288, right? So that's the product of LCM and GCF. Now, what were the two numbers that we were dealing with? 16 and 18, right? And if I go 16 times 18, I should also get 288. So the product of LCM and GCF, always the product of the numbers themselves. So sometimes if you know the LCM, in order to find the GCF, you just divide the product. Or sometimes to find the LCM is hard, but to find the GCF is easy. It's easy to find the common factor, so you take the full product, divide by the common factor, and you'll get the LCM. So that's kind of a sneaky way of finding the denominators. You take multiple of both numbers, then you divide it by the common factors, and that'll be the least common denominator. We're not going to prove this, but so LCM of two numbers times GCF of two numbers equals the product of two numbers. Okay? All right. So I think there are some LCM and GCF questions on this first homework. And the last thing I need to talk about factorization. Wow, it's hard to read what I'm writing here. What? You want me to stop? No, I got to talk about absolute values really fast. You like absolute values, right? Absolute value. You like absolute value. Are you with me on that? Because you can compute those really easily. What is absolute value of 5? 5. What is absolute value of 3? Negative 3? 3, right? That's easy. How do you know that? How do you know that absolute value of 5 is 5? Doesn't have to be. I can take absolute value of any real number, right? Who wants to answer that? How did you come to those answers? Square root of absolute value of 5 is 5. Absolute value of negative 3 is positive 3. Has to be positive, right? Is that what you're saying? Well, now think about how your brain worked. How did your brain compute that absolute value of 5 is 5? What was your thought process? Yeah, good. You look at 5. Well, it's positive to begin with, so I'm done. How about absolute value of negative 3? How do you make it positive? Well, how can you take away negative? Multiply by negative, right? So the absolute value is really a piecewise function. It's either a if a is greater than or equal to 0, or negative a if a is less than 0. So if a is negative, you make it negative of a negative, that makes it positive, right? Because if I get all kinds of mean on you and I ask you, what is the absolute value of square root of 5 minus 2? Keep in mind that absolute value does not distribute through pluses or minuses. It's not just making the minus in the middle into a plus. You have to ask yourself, is square root of 5 minus 2 a positive or a negative number? What do you think? Positive, because square root of 5 is bigger than 2, right? So if it's positive, then I don't need to mess with that. But if I ask you what is the absolute value of 2 minus the square root of 7, for example, is that a positive or a negative number? 2 minus root 7? Well, absolute value is, but how about just 2 minus root 7? Negative. You have to make it positive, so you have to multiply it by negative 1. Right? That's what this said. If number is negative, to make it positive, times it by negative 1. You distribute negative 1, you'll get square root of 7 minus 2. So this is how you compute absolute values of some of the fancy ones. Yeah. Now, here's a question from your homework, actually. I don't want to do that one. I'll do something very similar. How about, yeah, let's do that one. Pi squared minus 8 pi plus 16. Now, first, can I ask, can you factor pi squared minus 8 pi plus 16 when you have a 16 perfect square and then 8 in the middle, right? It's one of those pretty formulas. It factors into pi minus 4 quantity squared, right? If you just factor that's a perfect square. Now, do you remember how to take a square root of a square? What is that going to give you? Pi minus 4, but pi minus 4 is negative. Is that right? Can a square root equal a negative number? No. So this is a rule. When we take a square root of squares, just to make sure we toss absolute values around them. Because they always have to come out positive. Square roots are always positive. Now, pi minus 4 is negative. In order to take the absolute value of pi minus 4, you have to put a negative in front of that. So that gives you 4 minus pi. So that's the answer. All right. Well, you have, that's from your homework directly. You have a few more of these. Yeah. So basically, we have this rule somewhere here I'm going to write that square root of a squared is absolute value of a, just on the off chance that a is negative to begin with. You have to make sure it comes out positive. All right, good. I think, yeah, we're done. The Simpsons took too much time.